All right, so this is a continuation of our interactions previous video. This is the part two. So this is our third type of interaction. Our third type is explosions. So with things that explode, they're moving away from each other, right? So that means that they start together. So this is where two objects are resting together side by side, but then something happens and causes them to move apart. And for this equation, you'll see that for the equation, you'll see that the momentum is equal for each object. The momentum for the first one is equal to the momentum for the second one. And notice how there's no sign for one, but there is a sign for the other. So this is essentially positive, this one's negative, because they are moving away from each other. One will be moving to the right, so maybe this one move to the right, this one will move to the left. The total system momentum is conserved for collisions between objects in an isolated system. So in this isolated system where we have interactions, momentum is conserved for all three. That means that the momentum before and after is going to be the same for all of them. And as always, M1, M2 is for mass for each object. V1, V2 is for the change in velocity for each object. Okay, so with these explosions, we've already talked about it before, but if the masses are equal, because remember, they are applying those equal and opposite forces on each other, right? Newton's third law. They're equal and opposite forces. However, their acceleration differs based on their masses. So if the masses are equal, then their post-explosion, so over here, their after-explosion, velocity will be equal in magnitude. And that's assuming that the system is initially at rest. So these two carts here are initially at rest. You see that their masses, they are the same. They are 0.5 and 0.5 kilograms. So after the explosion, they both move 40 centimeters per second, 40 centimeters per second. However, notice that this cart moving to the right has a positive velocity. This cart moving to the left has a negative velocity. So equal in magnitude, but opposite in direction because they are moving away from each other. One to the left, one to the right. And then, of course, our masses won't always be equal. We won't always live in that perfect world where the masses of the objects are both 0.5. So if the masses of the objects are unequal, then they will have to be set in motion by the explosion with different speeds. Yet, even if the masses of the two objects are different, the momentum change of the two objects will be equal in magnitude. So you'll still have the same change in momentum, because remember, momentum is conserved. So, before the explosion, you'll notice that both velocities are 0. You have a cart, this yellow cart, which is 0.5. However, this red cart is now 1 kilogram. It has weight added to it up here. All of a sudden, they move apart. Again, they had equal and opposite forces acting towards each other, right? But masses. So, after the explosion on this right-hand side, notice that their velocities are different. So on the left-hand side, this yellow cart, the one with the less mass, this one is moving at negative 40 centimeters per second. However, if you look at the cart that was heavier, this 1 kilogram cart, it is only moving with a velocity of 20 centimeters per second to the right. However, the change in momentum will be equal. So what that means is both of them have a 0 momentum. After the explosion, they both have some sort of momentum. And it says that they will be equal in magnitude, that momentum change. So remember, momentum is mass times velocity. So 0.5 times 40, that's going to give you 20. And it was a negative 40, so it'd be a negative 20. The velocity, or the momentum for this red cart, momentum equals mass, so 1, times 20, a positive 20, so this would give us 20 for the momentum. So yeah, they are equal in magnitude, 20 and 20. They're just opposite in the direction, so negative 20, positive 20. Here are some more examples just to give you some more visuals. So here in this top example, we have a yellow cart, 0.5 kilograms. Now this red cart suddenly got more weight, and now it's 2 kilograms. And before the explosion, of course, they are both at rest, 0 centimeters per second. All right, then after the explosion. After the explosion, everything changes, right? Except for the mass. The mass is still 0.5 and 2. However, the 0.5, again, moves at negative 40 centimeters per second. But with the 2 kilogram cart, it only moves at positive 10 centimeters per second. And to prove again that our momentum change is the same, momentum is equal to the mass times the velocity. So 0.5 times negative 40 would give you negative 20 kilograms meters per second. And on our second cart, our red cart, our momentum is 2 for the mass times 10 for the velocity. So again, 20. One is positive, one is negative, but the momentum change is the same. It goes from 0 to 20, 0 to negative 20. All right, and you are more than welcome to analyze the one on bottom, and you can prove for yourself that the momentum is the same. So remember to find the momentum, mass times velocity for each one. All right, if you have any questions, leave a comment. Thanks.